Imagine standing in the middle of a desert. The sun is brutal. The wind carries sand that stings your face. The ground beneath your feet is dry, cracked, and seemingly lifeless. There is no river in sight, no shade, no soil worth speaking of, just sand, stretching as far as the eye can see in every direction. Now imagine someone walks up beside you, crouches down, and plants a seed. You'd probably think they were out of their mind. And yet, that is almost exactly what happened in the Mu-Us Desert in northwestern China. And what started as a desperate experiment, dismissed by many as impossible, has now become one of the most extraordinary agricultural stories of the 21st century. This is the story of how nearly 12,000 Chinese farmers, armed with ancient techniques, modern science, and an almost stubborn refusal to accept defeat, transformed 4,000 acres of barren, shifting desert sand into productive farmland, growing potatoes where nothing was ever supposed to grow. By 2023, those fields were producing over 1.7 million kilograms of potatoes every single year. And the world has taken notice. Agricultural delegations from Saudi Arabia, the United Arab Emirates, and several other nations have already made their way to this once-forgotten stretch of desert. Not to see ruins or monuments, but to understand how food was grown where it had absolutely no business growing. Welcome to Hems Reports. I'm Mike. And today, we're diving deep into one of the most remarkable stories of human ingenuity on the planet. To understand why this potato story matters so much, you first need to understand what China has been dealing with for decades. A desertification crisis of almost incomprehensible scale. Desertification is not simply the expansion of existing deserts. It is a slow, creeping process by which productive land that once supported farming, grazing, and communities, gradually degrades into dry, infertile terrain that can no longer support life. It happens through a combination of climate change, overgrazing, deforestation, and poor land management. And once it sets in, it is extraordinarily difficult to reverse. For China, this was not a distant threat. It was, and in many regions still is, a daily reality. At its worst, China's desertified land area reached approximately 2.622 million square kilometers. To put that into perspective, that is an area larger than the entire country of Algeria, the biggest country on the African continent by land area. This desertified territory represented roughly 27.4% of China's total landmass. More than a quarter of the country was essentially unproductive, dry, and hostile to agriculture. The consequences were devastating, and they played out not just in remote regions, but in cities and towns hundreds of kilometers away. The vast northern deserts of China acted like a sand factory. Whenever strong winds came sweeping down from the north, which they did with increasing frequency, they picked up millions of tons of loose sand and carried it across the country in the form of massive dust storms. These were not minor inconveniences. These were catastrophic weather events. Sandstorms would descend on cities with little warning, turning the sky orange and reducing visibility to nearly zero. Highways were buried, crops were destroyed overnight, livestock suffocated, people died. Communities that had farmed the same land for generations found themselves slowly being swallowed by an advancing wall of sand that moved a little further every year. In rural areas bordering these desert zones, life became increasingly desperate. Farmers watched their fields shrink. Families packed up and left. Entire villages were abandoned. The human toll was enormous, not just in economic terms, but in the psychological weight of watching your homeland disappear. This was the scale of the challenge China faced, and it demanded a response that was equally large in scale. Beginning in the late 1970s and accelerating significantly in the early 2000s, China launched one of the most ambitious environmental restoration campaigns in recorded human history. The centerpiece of this effort was a massive afforestation program, the planting of trees in and around desert regions to act as windbreaks, stabilize the sand, and gradually restore soil quality. Known in some circles as the Great Green Wall, this was not a single project but a collection of interlocking government initiatives that spanned decades and involved hundreds of millions of people. Since 1988, China has been systematically planting trees in desert and semi-desert regions across the country. The numbers involved are staggering. To date, China has successfully planted more than 100 billion trees in and around these arid zones. That is not a typo. 100 billion trees. The effort has effectively improved approximately 280 million acres of desert land. In addition to tree planting, the government established 41 comprehensive demonstration zones for desertification prevention and control spread across the most vulnerable regions of the country. These zones served as living laboratories, places where scientists and local communities could experiment with different approaches to land restoration and share what worked with the wider world. The government also implemented closure and protection policies on massive sections of land, essentially fencing off 26.58 million acres of desertified land and prohibiting further human activity that might damage the fragile recovery process. By giving the land time and protection, nature was allowed to begin healing itself, aided by the tree planting efforts surrounding it. The results of all these combined efforts have been remarkable. China achieved what experts described as a historic reversal, the point at which green vegetation began advancing where sand had previously dominated. For the first time in generations, the deserts were retreating rather than advancing. This achievement earned China recognition and praise from international environmental organizations, and its techniques have been studied by countries facing their own desertification crises across Africa, Central Asia, and the Middle East. But here is the thing. As incredible as the Green Wall story is, it is almost overshadowed by what came next. Because planting trees in the desert is one thing. Growing food in the desert? That is something else entirely. If you pull up a satellite map of China and look toward the northwest, you will notice a large expanse of yellowish-brown terrain sitting in a region that straddles the border between the Inner Mongolia Autonomous Region and Shanxi Province. That is the Mu-Us Desert, one of the 4 major deserts in China, and for a very long time, one of the most troubled stretches of land in the entire country. The Mu-Us Desert covers an area of approximately 42,200 square kilometers. That is roughly the size of Switzerland, or slightly larger than the Netherlands and Belgium combined. For most of its modern history, this desert was known for 2 things: the sandstorms it sent howling toward nearby cities and villages, and the extreme poverty of the communities forced to live on its edges. Year after year, the shifting sands would advance on farmland, burying crops, destroying irrigation systems, and reducing productive land to worthless terrain. The region had almost no economic base to speak of. The people who remained were among the poorest in China. Opportunity was scarce. Hope was scarcer. Rainfall in the Mu-Us Desert averages between 250 and 440 millimeters per year. To put that in context, London receives about 600 millimeters annually. New York gets around 1,200 millimeters. Even regions typically described as semi-arid receive more rain than the Mu-Us. In agricultural terms, rainfall below 500 millimeters per year is generally considered insufficient for most staple crops without irrigation. The Mu-Us, in its natural state, simply could not support farming on any meaningful scale, or so everyone thought. The first attempt to push back against the Mu-Us Desert did not begin with potatoes. It began with trees. In 2016, a team of Chinese scientists and agricultural engineers began working in the desert, using an approach they called the minimally invasive planting method. The concept behind this technique was, honestly, elegant in its simplicity. Introduce vegetation to the desert in a way that disturbs the existing environment as little as possible, maximizing the chance that the planted trees would actually survive. Traditional tree planting in arid regions often involves deep excavation, heavy irrigation infrastructure, and significant soil disruption. all of which can actually make things worse by further destabilizing the sandy surface. The minimally invasive method, by contrast, used precise, targeted intervention. Small holes were drilled into the sand. Drought-resistant saplings were inserted at the right depth to access whatever moisture lay below the surface. The surrounding sand was carefully packed to reduce evaporation. And then, patience. Remarkably, it worked. The saplings took root. They grew. And as they grew, their root systems began doing something extraordinary. They started binding the sand together, slowing the movement of the dunes, and creating tiny pockets of shade and moisture that altered the microclimate of the surrounding area. The farmers living on the edges of the desert watched all of this with intense interest. If trees could survive here, could crops? Some of them decided to find out. Working alongside the scientists, local farmers began running small, informal experiments, testing which crops might tolerate the harsh conditions of the MUUS. Most attempts failed, but a few showed promise. And among those, one crop kept standing out: the humble potato. The potato is, in many ways, the perfect desert crop candidate. It is hardy. It requires less water than many other staples. It can tolerate a wide range of soil conditions. It has a relatively short growing cycle, which means it can be harvested before the worst of the desert's seasonal extremes hit. And critically, it provides dense caloric value, more food energy per kilogram than most grains. But early results were underwhelming. The yields were low, maybe 5 to 6 times lower than what the same farmers could achieve on ordinary farmland. The potatoes grew, yes, but barely. To make this a viable operation, something fundamental had to change. The science had to get serious. In 2018, two things happened that changed the trajectory of this project forever. First, the Chinese government dispatched a formal scientific team to the MUUS Desert to conduct a thorough, systematic analysis of the soil and climate conditions across different parts of the desert. This was not a small survey. This was a rigorous, multi-site study designed to answer one critical question: which areas of the MUUS, if any, had genuine agricultural potential that technology could unlock? The results were more encouraging than many had expected. The scientists found that while the desert as a whole was hostile to agriculture, specific zones within it had underlying soil characteristics: mineral composition, moisture retention at depth, topographic position, that could, with the right interventions, support crop production. The desert was not uniformly hopeless. It was patchy in its potential, and the patches that showed promise were significant in area. Armed with this scientific foundation, the local government made a bold decision. In October 2018, officials announced a commitment of approximately $350 million, a massive investment, to fund an ambitious program that would attempt to convert qualifying desert land into productive farmland at scale. This was not a scientific pilot. This was a national-level commitment to proving that desert agriculture was not just a dream, but a deployable strategy. The funding unlocked resources that the earlier scrappy experiments had never had access to: proper irrigation infrastructure, soil enrichment materials, technical support for farmers, and the organizational capacity to coordinate work across thousands of acres and thousands of people. This is the part of the story that most people find genuinely surprising, because the answer involves a technique that is simultaneously thousands of years old and brilliantly suited to modern applications. The core challenge of desert agriculture is water. Without water, nothing grows. And in a region receiving as little rainfall as the MUUS, there is simply not enough precipitation to sustain crops through ordinary rain-fed agriculture. So, how do you get water into a desert at scale? The answer the Chinese scientists and farmers arrived at was flood irrigation. Now, flood irrigation sounds counterintuitive when you are talking about a desert. Floods and deserts seem like they belong to entirely different worlds. But here is the geography that makes it possible. The Mu-Us Desert is not entirely isolated from water sources. It sits in a region where seasonal rivers and their tributaries swell significantly during certain times of year, particularly during monsoon season and periods of heavy upstream rainfall. The technique involves deliberately channeling these seasonal floodwaters into the desert areas designated for agriculture. Carefully constructed earthworks and channels guide the water across the designated farming plots in a controlled manner. The water floods the surface, saturating the sandy soil to a meaningful depth. But here is the part that elevates this from simple irrigation to something truly clever. When floodwaters move across a landscape, they carry sediment, silt, clay particles, organic material, all of it suspended in the water. As the water spreads across the desert surface and slowly percolates down through the sand, it deposits this sediment in and around the sand particles. Over time, and it does take time, this silt deposition begins to transform the character of the soil. The pure, dry sand starts to develop a more complex structure. It gains water retention capacity. It accumulates organic matter. Nutrients arrive and begin to concentrate in the upper soil layers. The ground, in essence, starts to behave less like desert sand and more like real agricultural soil. This is an ancient principle. Civilizations along the Nile, the Tigris, and the Euphrates have understood for millennia that floodwaters enrich the land they touch. What makes the Chinese application of it in the Mu-Us remarkable is the precision and intentionality with which it was deployed on a massive scale in a modern context. Starting in 2019, a coordinated team of about 12 agricultural experts and a growing group of local farmers began working together to apply this flood irrigation technique across experimental plots. Their initial focus was a carefully selected 20-acre test area, small enough to monitor closely, but large enough to produce data with real statistical significance. The first harvest results from this 20-acre experiment told an important story. The team successfully brought in 3,000 kilograms of potatoes. That's an average of about 150 kilograms per acre. Compare that to the yield on normal Chinese agricultural land, which can reach 700 to 1,000 kilograms per acre under good conditions, and you can see the desert was still yielding far less. The gap was real. The yield was roughly 5 to 6 times lower than conventional farmland. But here's what mattered. The potatoes had grown in a desert, without traditional soil, on land that just years earlier had been considered completely and permanently unproductive. The method was feasible. The question now was whether it could be improved. The success of the initial 20-acre experiment was not the end of the scientific journey. It was actually the beginning of its most intensive phase. Chinese agricultural researchers poured their energy into understanding why yields were low and what could be done to raise them. Every variable was analyzed: the depth and timing of flood irrigation cycles, the specific varieties of potatoes best suited to the sandy, nutrient-light soil, the spacing of plants, the use of organic amendments to accelerate soil enrichment, and the management of sand movement to prevent newly transformed plots from being buried by drifting dunes. Gradually, the improvements accumulated. Yields per acre climbed steadily. The 150 kilograms per acre of the early experiments began to rise, not to the heights of China's best agricultural land, but meaningfully higher, crossing 200, then 300, and eventually approaching 430 kilograms per acre by the time the project hit its stride. Meanwhile, the project expanded dramatically in geographic scope. What had started as a 20-acre experiment grew to cover nearly 4,000 acres of desert land across the Mu-Us. This was no longer a scientific pilot. This was industrial-scale desert agriculture. To manage this scale, the project needed people, lots of them. And this is where the human story of the Mu-Us becomes particularly compelling. The government and project organizers actively recruited local farmers from surrounding villages to join the initiative. These were people who had spent their lives watching the desert claim the land their families had farmed for generations. They had every reason to be skeptical. Many of them had already accepted that farming the Mu-us was not a viable future. But the early experiment results gave them something they had not had in a long time: reason to try again. According to project records, nearly 12,000 farmers became participants in the Desert Agriculture Program. They were not simply laborers, they were partners in the agricultural process, bringing their intimate local knowledge of the terrain, the wind patterns, the seasonal rhythms of the desert, and combining it with the scientific guidance provided by the research team. The collaboration between farmers and scientists was genuine, and it showed in the results. By 2023, the combined effort of those 12,000 farmers and the scientific teams backing them produced an outcome that generated headlines across the global agricultural community. The Mu-us desert potato fields yielded over 1.7 million kilograms of potatoes in a single year. 1.7 million kilograms from a desert in 1 year. It was a world record, and more importantly, it was a proof of concept that no one could dismiss. Statistics are important. They communicate scale. But they can sometimes obscure the most fundamental truth of a story like this one, which is not about kilograms or acres or investment figures. It is about people. The Mu-us desert region was, for decades, synonymous with poverty. The communities living on its margins had some of the lowest incomes in all of China. Agriculture was barely viable. Young people left for cities as soon as they could. The elderly who remained did so not out of choice, but out of circumstance. Villages were hollowing out, physically and socially. The Potato Project changed that equation. As the farming operations scaled up and yields improved, participating farmers began to see their incomes rise in ways that most had never experienced. According to figures from the project, the annual income of some participating farmers exceeded $10,000 per year, a figure that, in the context of a rural desert community in northwestern China, represented a transformational improvement in living standards. For context, average rural incomes in China's less developed regions had historically hovered at a fraction of that amount. The Desert Agriculture Program did not just feed people, it enriched them. But the transformation was not purely financial. As the farmland expanded and the sand was stabilized by both the potato crops and the trees planted alongside them, the physical environment of the region began to change visibly. Sandstorms became less frequent and less severe in the areas surrounding the managed farmland. The air quality improved. Roads and infrastructure that had previously been buried and damaged by drifting sands became more durable and reliable. Families that had left the area in previous decades began, in some cases, to consider returning. The government reports that today, nearly 94% of the Mu-us sandy land has been brought under effective management. That is an astonishing figure for a region that, within living memory, was considered an irreversible environmental disaster zone. More than 30 villages surrounding the Mu-us have seen their quality of life improve measurably as a direct result of this combined ecological and agricultural transformation. Schools, healthcare, and basic services that had been difficult to sustain in depopulating communities have found new purpose as the population stabilizes and, in some areas, grows. This is what sustainable development actually looks like, not on a conference stage or in a policy document, but on the ground, in people's homes, in their children's futures. To fully appreciate what has been achieved in the Mu-us, it is worth pausing to understand the science of what happens when flood irrigation is applied to desert sand over time, because the transformation is not instant and it is not simple. When water is introduced to dry, loose desert sand, the first thing it does is occupy the air spaces between sand particles. This provides immediate temporary moisture that plants can access through their root systems. But in pure sand, without silt or organic content, this moisture drains away quickly, often within hours or days, because sand has very poor water retention capacity. This is why plants typically struggle and die, even in desert regions that receive occasional rainfall. The genius of the flood irrigation approach is that it does not just introduce water, it introduces water-carrying sediment. As the floodwaters slow and spread across the desert surface, the heavier particles, sand, silt, clay, begin settling out. Over multiple irrigation cycles, layers of finer material start to accumulate within and above the desert sand. Clay particles, in particular, dramatically improve soil water retention. They are much finer than sand grains, and they fill the gaps between them, creating a matrix that holds water far more effectively. Organic matter from plant debris carried by the floodwaters adds further complexity, providing the microbial community that healthy soil depends on. In parallel with this, the root systems of the planted trees and potato crops themselves contribute to soil development. As roots grow, they break up compacted sand layers, create channels for water to penetrate more deeply, and, when they die and decompose, add organic carbon directly to the soil profile. After several cycles of this process, what was once pure desert sand begins to exhibit the characteristics of genuine agricultural soil. Better water retention, improved nutrient content, a developing microbial ecosystem, and greater structural stability. It is slow. It takes years. But it is real. And it is permanent in ways that simple irrigation without sediment loading would never be. This is why the specific geography of the Mu-Us, its proximity to seasonal rivers with significant sediment loads, is so important. Without a nearby source of silt-laden floodwater, the transformation the Chinese achieved simply would not have been possible in the same way. The potato was the entry point, but it was never meant to be the whole story. Once the potato project had demonstrated that food production in the Mu-Us was viable, the participating farmers and scientists began experimenting with other crops. This was a natural and logical evolution. No regional food system can depend on a single crop, and diversifying product